This is the third and final mini lecture of the week. We'll discuss why conformal symmetry is a loophole to the Coleman-Mandula Theorem. It provides a non-trivial way to extend the Poincare group, and as such it suggests it's a very interesting symmetry to think about, and indeed we'll learn in the first half of the module why conformal symmetry is such an interesting subject to study in and of itself. So, conformal symmetry. So we'll see shortly that scale transformations that change your notion of distance in a physical theory, are a generator of the conformal group. And these scale invariant theories are another loophole. They're another loophole in the Coleman-Mandula Theorem. So why do I say that? Well, if you look in detail at the proof, which unfortunately we're not going to do in this course, you'll see that the proof requires the assumption that there's an S matrix or a scattering matrix, something that has the detail of all the scattering processes in the theory, how two particles come in, interact, and then go off to infinity. And in these scale invariant theories, it's very difficult to define an S matrix. And because you don't have an S matrix in scale invariant theories, then you can't prove Coleman-Mandula for these scale invariant theories. Let me try and give you a little bit of intuition for why that might be. There's difficulty in defining asymptotic states. So what are these asymptotic states? To define the S matrix, you have some particles in the far past. They're so far apart that they don't interact. They come in, they scatter, and they go off to the far future, where again they're so far apart that they don't interact. So in these scale invariant theories, the problem is that these asymptotic states don't exist. There are no asymptotic states that are asymptotically far apart and hence non-interacting. You can always do some scale transformation and bring those asymptotic states back close together again, and so there's no real notion of far. There's another way of explaining this which might make a little bit more, or might be a little bit more familiar to you. If you studied scattering processes in quantum mechanics that involve a Coulomb potential. So if you remember the Coulomb potential, this is mediated by the photon, which is a massless particle. So it doesn't introduce the scale to the theory, and therefore you can have scale invariant theories that have forces mediated by photons. So you remember from our discussion last week, in relativistic quantum field theories, mass and length are basically related. Mass is like 1 over length. So if you have scale transformations in distance, that's equivalent to scale transformations in mass or energy as well. So with these photons and the Coulomb potential, if you've done a scattering calculation in quantum mechanics, you might have seen that the total cross-section for Coulombic scattering is infinite. And that's very closely related to why there's problems in defining an S matrix in theories with conformal symmetry, that these forces mediated by massless particles have very long range. And it's hard to get these asymptotic states where the forces die off and you can think about the particles becoming independent again. And so again, you don't have an S matrix in these conformally invariant theories, and so you can't prove Coleman-Mandula. And therefore, in these conformally invariant or these scale invariant theories, you can non-trivially extend the Poincare group. So that's all I want to say about the loophole. And I could end the lecture here, but I want to take advantage of your presence to try and explain to you what the conformal symmetry group is. And so that the rest of the lecture is now going to be a discussion of what is conformal symmetry. So it's very simple to define. It's the set of coordinate transformations which leave the Minkowski tensor, or more generally a metric, invariant up to a position-dependent rescaling. So I have my new Minkowski tensor, and I use my rule for how to implement diffeomorphisms. I can write it in terms of the old one as some derivatives with respect to my coordinate transformation times my old one, contracted with my old one. And the claim is that that has to be a local function of position. Let's call that big omega of x times the Minkowski tensor eta alpha beta. Actually, now I have to make sure the indices agree, so that's eta mu nu. Okay, it's the set of transformations x goes to x prime or x prime goes to x, which have this property. So it's a little bit more general than Poincaré. Poincaré is the set where omega equals 1. Here we're allowing omega to be some non-trivial function. So let's just say that. Poincaré is a subgroup. In particular, it's the subgroup with omega x equals 1. So you don't change the Minkowski tensor, and so you therefore don't change the notion of distance, as we discussed in the first lecture this week. I said before that scale transformations were an important generator of Poincaré, so let's see how that works. What is a scale transformation? It's a coordinate transformation that just rescales all the coordinates. I send x mu to some constant times x mu. And this is my new x prime of mu. And so therefore, if I take this derivative, dx alpha dx prime of mu, this is a Kronecker delta, delta alpha mu, times, well, 1 over lambda, since I've switched it so that x prime is on the bottom. And this implies, by our definition on the previous page, that the function omega is actually just a constant. It's 1 over lambda squared. So scale transformations fit this definition. There's another important set, which we'll get to in a moment, the so-called special conformal transformations. But in order to get there, I want to sort of prove what the most general possible set of these conformal group transformations are. Okay, before we get there, let me make a couple of remarks. First remark, the Jacobian of my transformation and the scaling factor omega are related. I can just take a determinant of both sides of this defining relation. I'm going to get the determinant of the coordinate transformation, that is the Jacobian, dx alpha dx prime mu. There were 2 of these, so I get 2 factors of the Jacobian, dx beta dx prime nu, and then multiplied by the determinant of eta alpha beta, and this must be equal to the determinant of omega times eta mu nu, which I can write as the determinant of eta mu nu times a dth power, where d is the dimension, the space-time dimension of this scale factor omega. So the determinants cancel from both sides. This little factor here, this is the Jacobian. And so I learn what? I learn that the Jacobian squared is this scale function omega to the dth power. That's my first remark. Second remark, what is this word conformal? Why do we use the word conformal? So conformal means the angles don't change. So if we think about the Euclidean case for a minute, where the Minkowski tensor is just a Kronecker delta function, I don't have a separate time coordinate, all the coordinates look spatial, and I have 2 vectors, I'll call it v and w, and there's some angle between them. I know if I take v dot w over the norm of v and the norm of w, going back to some pre-college facts, that's just the cosine of the angle between those vectors. But the point here, why do I bring this up? Well, you have the same number of factors of the metric of the Minkowski tensor in the numerator and the denominator of this fraction. You've got one factor of the Minkowski tensor up top, and you've got a half here for this norm and a half there for that norm. And so the factors of omega cancel, and theta remains invariant under the transformation. So angles don't change under conformal transformations. That was the second remark. Okay, so now let's try to be more general and thorough. Let's try and construct the most general possible conformal transformation, and that's going to take up the majority of this lecture. We'll do it infinitesimally. We'll try and look at the Lie group. That's usually a good way to approach, we'll try to look at the Lie algebra. That's usually a good way to try to understand the Lie group. Once we have all the infinitesimal elements, we can reconstruct the finite ones. So infinitesimally, it's like our discussion of Poincaré. We're going to start with how it acts on space-time. We have x goes to x prime mu, which is our old x mu plus a small shift, epsilon mu of x. And we're going to assume this thing is small. This epsilon function is small, okay? So we have our defining relation that eta prime of mu is dx alpha dx prime mu, dx beta dx prime nu, eta alpha beta. And so expanding that out to first order, we find that eta mu nu goes to eta mu nu minus a shift, d mu epsilon nu plus d nu epsilon mu. Notice the minus sign, because again, I've kind of inverted it. I'm taking the derivative of x with respect to x prime instead of vice versa, so I've got to move the epsilon over to the other side. And then plus some small corrections that I'm going to drop, because I'm just looking infinitesimally. Now, because of the definition, right, this little change has to be related to this local function omega somehow, so let's let omega, what's going to be close to unity, since it's a small element, plus some small shift f of x. Okay, and now we can identify these derivatives of epsilon with f of x times the Minkowski tensor, okay? So this is our starting equation. This is the workhorse. We're going to keep coming back to this again and again. And so let's give it a name here. Let's call this the happy face equation for this lecture. And I'll refer to it as such as we proceed. First step, take a trace. We take a trace. On the left-hand side, we get 2 d mu epsilon mu. On the right-hand side, we get a d from taking a trace of the Minkowski tensor. So let's move that back over to the left-hand side. So this is going to be f of x. So f of x is related to the divergence of this epsilon tensor. So now what I want to do is I want to do some more, more machinations with these simple equations to try and get to some conclusions. It's going to take us a little bit of time, but just bear with me. Every step is very simple, and then somehow magically all these little simple steps come together nicely at the end. So I've copied the happy face equation. Our next step is to consider a further derivative of this, d rho. And we're going to do it in a very particular way. We're going to consider some of our permutations of the derivative. So we'll look at d mu of d nu epsilon rho plus d rho epsilon nu minus f eta nu rho plus d nu of d mu epsilon rho plus d rho epsilon mu minus f eta mu rho. And then finally minus d rho of d mu epsilon nu plus d nu epsilon mu minus f of eta mu nu. So this has to be 0 because each of those terms in parentheses is our original happy face equation, and I'm just taking a derivative of each of those. And if I sum it up, I've cleverly arranged it so a bunch of terms cancel out, and what survives is what? It's 2 d mu d nu epsilon rho is equal to eta nu rho d mu f plus eta mu rho d nu f minus eta mu nu d rho f. Okay? These are the only 4 terms that survive from the original 9. And so now, what do we want to do? We want to take a trace again, contract with the metric tensor, contract with the Minkowski tensor, and we see what we get. We get 2, the Laplacian acting on the epsilon vector is equal to 2 minus d mu f. Okay, we're slowly getting somewhere. Bear with me a few more minutes and we'll get a big payoff. But this is going to be another important equation for us. I'm going to call this the Boat equation. And I'll just notice from this that there seems to be already something special about 2 dimensions, and that is in fact true. Conformal field theories in 2 dimensions are very special objects. And I really wish I could say more about it in this module, but I don't have the time or the space. I'll probably assign a few exercises here and there about it, but I just point that out here that there's clearly a very distinct difference or different path we could take at this point where the right-hand side of this equation vanishes for 2 dimensions. Okay, so we have this. We're going to take this Boat equation. We have this Boat equation. What I want to do is I want to take a symmetrized combination, d squared of d nu epsilon mu plus d mu epsilon nu is equal to 2 minus d mu d nu of f. So I take, another derivative, either a mu derivative. I see I have a mistake here. Dreadful. Have a mu index on both sides, right? So I can take either a new derivative of the equation with a mu index or a mu derivative of the equation with a nu index, add them together, and I still expect this equality. And now I want to compare this. So this becomes that. And I want to compare this with our happy face equation. And you notice, what's in the parentheses is what's on one side of our happy face equation. And so we can replace that with f. And what we learn from this is what? We learn that 2 minus d of d mu d nu f is equal to d squared of f times eta mu nu, the Minkowski tensor. And I'm going to take a trace. We're almost there. You bear with me just 30 more seconds. We take a trace, and we learn from taking a trace that d minus 1 of d squared of f equals 0, and I plug this back into the equation one line above, and I learn what? That the second derivative d mu d nu f is 0, not just the Laplacian, but d mu d nu f in general for any choice of indices mu and nu is 0. And this is all again provided d is not equal to 2. Okay, so we're basically there. So we learn a very important fact. We learn that f is at most linear in the space-time coordinate. And since f is a derivative of epsilon, we learn that epsilon is at most quadratic in the space-time coordinate. A mu plus b mu nu x nu plus c mu nu rho x nu. Okay. So that's the central result here. That's the central result. We've learned that epsilon has a very constrained form given this definition of what a conformal symmetry transformation is. We can say a little bit more about epsilon. Well, first something obvious. Because we're contracting that c mu nu rho object, that 3 tensor with something that's symmetric in the x's, we know it really only makes sense to think about some object there, c, which is symmetric in the last two indices, that c mu nu rho is the same as c mu rho nu. And now what we're going to do is we're going to plug this back in. We're going to combine this with our smiley face equation. We're going to find some further constraints on these tensors. And this I leave as an exercise for you to think about offline. So for a mu, there's no constraints. You can choose whatever vector you want. That shouldn't be a surprise. These are just the translations, which are part of the Poincare group, which we know is a subgroup of the conformal symmetry group. B mu nu, this 2 tensor, has 2 pieces. There's a lambda times the Minkowski tensor plus omega mu nu with omega mu nu antisymmetric. So these are just the Lorentz generators. Again, that's no surprise. They had to be there. We knew Lorentz is a part of Poincare, which is a subgroup of conformal symmetry. And we saw before that these scale transformations had this form that correspond to this choice of b mu nu, which is lambda times the Minkowski tensor. So lambda are the scale transformations. So that's not a surprise. They're often given another name in this business. People call them dilatations. Scale transformations are dilatations, the same thing. And finally, we've learned something new. There's these guys that are quadratic in the x's, the c mu nu rho. These actually only depend on a vector. The only thing consistent with the transformation law is to let this 3 tensor actually be a vector. I can write that as Minkowski tensor times b, Minkowski tensor with the indices scrambled a little bit, times b, and then same thing again. And b mu is a constant vector. And these are what I promised before. These are the special conformal transformations. And that's the conformal symmetry group at an infinitesimal level. It's generated by translations, by scale transformations, by Lorentz generators, and by these extra guys that may be quite new to you, these special conformal transformations, which corresponds to choosing some vector b. Let's try to put a little bit more meat on this. Let's write out explicitly what this special conformal transformation looks like when it acts on a coordinate. So it will send x mu to x prime mu, just following the rule that we had on the previous page. So that's x mu plus 2 times x dot b, x mu minus b mu x squared for some infinitesimal vector b. That's the infinitesimal version of the special conformal transformations. So now we should integrate those up and get the finite versions. I'm not going to do that. I'll just give you the answer. It's easier that way because once you have the answer, you can always go backwards. You can make the finite version infinitesimal much more easily than you can make the infinitesimal version finite. A lot of these you know already anyway. Translations are exceptionally simple, right? It's just a shift of x mu by a constant vector. Lorentz, you've no doubt seen these rotations and boosts. We could write it as x prime mu equals some matrix, 4 by 4 matrix, acting on the 4 vector of the position. Dilatations, we also wrote down before. The finite version, we just rescale the coordinates. X prime mu is lambda x. And then finally, the new ones, the special conformal transformations, they're the ones that look fairly complicated. I have x mu minus b mu x squared over 1 minus 2 b dot x plus b squared x squared. So I leave you as an exercise to recover or to check that this is correct. So recover the infinitesimal versions from the finite ones. I'd like to make a remark that these special conformal transformations are a bit ugly, well, as you just saw. And there's a way to make it a little bit nicer, to clean up the notation. You can introduce a new element, a discrete element, which is called inversion. So it sends x mu to x prime of mu, which is x mu over x squared, and I squared just squares to the identity. So you don't get anything new after you apply it once. And these special conformal transformations can be written a bit more simply. It's I composed with translation, composed with inversion again. So that's a slightly nicer way to think about special conformal transformations sometimes. Okay, let's keep going. So like for Poincaré, we need a more abstract presentation. So remember, for Poincaré, we had the change in the space-time coordinate was given by acting with momenta plus acting with Lorentz plus, and now since this is not just Poincaré, it's Poincaré plus conformal, I also have to act with the special conformal transformations, the Ks. People usually use the element K. And then also the scale transformations, for which people also often use the capital letter D for dilatation. Now, if we just think about this, how these act on functions, well, as usual, we can think of p mu as minus partial derivative and m mu nu as this peculiar combination, x mu d nu minus x nu d mu. It's basically it's angular momentum, right? So it's r cross v. It's the cross product of the position and the velocity. So that's as before, but now we're also going to have dilatations, which we can write as minus I x mu d mu, and we can write special conformal as minus I 2x mu x nu d nu minus x squared d mu. And now given these, we can work out the commutation relations, just like we did for Poincaré. So we're going to have all the old Poincaré commutation relations like we had in the first lecture this week, but now we're going to have a couple of new ones. And so let's write those down, some new commutation relations. We're going to have dilatations with momentum. This is momentum again. We have dilatations with special conformal. This is special conformal again, but with the opposite sign. We'll see next week how that change in sign, the plus and the minus, is really of crucial importance for how you generate representations of the conformal symmetry group. D commutes with Lorentz. K commutes with itself. Lorentz with special conformal. This gives you a special conformal again. This should be reminiscent to how Lorentz commutes with momentum. That commutator has a very similar structure to this one. And then finally, the most complicated is how momentum and special conformal fail to commute. So you get minus 2i here, eta mu nu times the dilatations or scale transformations plus Lorentz. And so we'll just point out some obvious facts here, that P and K do not commute and P and D do not commute. So this is a violation of Coleman-Mandula, right? Where these extra symmetries, these extra generators of symmetries should all commute with momentum, and here they obviously don't. So we've non-trivially extended Poincaré. And we've also violated Coleman-Mandula, seemingly. Let's put that in quotes since we haven't really. We've also violated one of the assumptions that went into the proof, so since it's not consistent with the assumptions, the proof doesn't hold. I'll point out one thing before flipping the page and bearing these commutation relations. If we look just at d p mu and m mu nu, and forget about the k's, we see we have a closed algebra. Right, if we just look at the commutators that involve d and p and m, so that would be this one, and I guess that's it, right? All the other ones have k. I'm not generating k with these commutation relations. So these actually form a closed subalgebra. I don't, strictly speaking, need to augment scale transformations with special conformal. So let's say it again. It's sort of an important point. D, P mu, and M mu nu form a subalgebra. We don't require K mu for closure. But that said, it experimentally or physically, it turns out to be difficult to find interesting examples without the special conformal transformations that do have scale invariance, but then fail to also include the special conformal transformations. In 2 dimensions, there's some sense in which it's just impossible, also in 4. And more generally, one seems to find that these examples are non-unitary, or they have an unbounded spectrum. They have states with arbitrarily negative energy, for instance, or other problems that make them less interesting theories to consider. But that said, it's still sort of difficult to prove that if you have scale transformations, in which setting must you also have special conformal transformations. Okay. I want to make one last remark before ending here. Last remark. Let's count the number of generators. Let's see how big the conformal symmetry group is. So we have one scale transformation or dilatation. We have D translations, one for each direction. We have D special conformal transformations, again one for each direction. And we have D times D minus 1 over 2 elements of Poincaré. So if we add all those up, we find at the end of the day we have d plus 1 times d plus 2 over 2 generators. And so the number of generators, it's the same as the group SOD plus 2. And this is not an accident. The conformal group is SO d comma 2 if you include time, if you have a time coordinate, if you have a signature, 1 comma d minus 1, or it's also SOD plus 1 comma 1 in the Euclidean case where time is just like any of the other coordinates. So I've left this for you as an exercise to see this in detail, to see how the generators can be put in a more standard form that's should be familiar to you from the SOD rotation group. All right, that's the end of lecture 3 and the end of the lectures this week. There's a lot of material. Next week we'll come back and we'll think in more detail about the constraints of conformal symmetry and how conformal symmetry acts on quantum fields. Very good. See you next time.